us about flow categories. So take it away.
Okay, and hello guys. So today our work is mainly to discuss the paper. Oh, sorry, I should open it. Yes. Is to discuss the paper of flow categories and exact Lagrangians. By Pacelli and Smith. So I remember that in the last time, Philip, his work is also to read the paper by Pacelli, and he mentioned that it's a super good paper. And what I want to say is that this paper is also a super good paper. And I think they are really good at explaining things. I hope I can explain things to you as good as them today. So as there are plenty of details in the paper, today I will try to explain everything in the most intuitive way. And if you have any questions, and if you missed my words, or because of I have a little accent in English, so just interrupt me and ask your questions. So let's start. So there are three parts of today's talk, and first I will explain you everything in the more theory setting, and then come to the general setting. Even it's divided into the three parts, but the first part it contains almost everything, and what you need to do is to understand everything in a more setting. So today, when we discuss more theories, we assume all the transversality and everything is a manifold. So we don't discuss the non-generic case. And let's review what a Morse theory is. So we begin with a manifold with a Morse function, and I use this to denote the critical points. So we have an index map from the critical points to the indices of their hashing. And then we can define the modular space. I consider all the flow lines from a critical point to another critical point. And so this bar means that we modular the lateral R action of it. This is a manifold of dimension x, the index of x minus index of y minus 1. So besides this, we have the compactification of the modular space. So we know that when we are studying the gradient flow lines from x to y, and when it goes very close, it goes very close to y, it will break into two pieces. Yeah, so this is the standard Morse theory, and now let's translate it into abstract language. So so we still consider a manifold with a Morse function on it, and we can define a category M by considering its critical points as objects, and we define the index map as a gradient on the objects, and we define the morphisms between x and y to be the modular space between x and y, denoted as mxy, and so the compactification process is translated to the embedding of the manifold here. Yeah, so here is a picture of what I said. So consider this guy is T2, the torus, and we glue the left side and the right side, the upside and the downside, and consider such a function with. So we may say that the red curves in this picture are the flow lines, and the green curves are the level sets. So this is a flow category corresponds to this example, and it has 4 objects: the P, U, V, and Q. And so the flow lines from P to U are these 2 gradient flow, are these 2 trajectories. So I use 2, after moduling R, it becomes 2 points. And I use blue I use the blue color to present them. And the trajectories from P to V, they are also 2 points. So yeah, the same for trajectories from U to Q and V to Q. But the trajectories from P to Q, it has 4 connected components. Yeah. And the compactification of each connected component is a segment. And we have the embedding map from the compactification, which maps the product of these blue points to here the 4 blue points, and here the 4 black points, their product to these 4 black points. So this is a flow category of this example. And any questions about the definition? So good. So let's continue.
I'm kind of confused.
Okay.
Like the map is a map of objects, like on M.
Yes.
So it's like not. I
Yes.
can't give. I can't like if you give me a category, I can't know that it's like a Morse category. Like it's kind of weird.
So it's not just a category. It's a category with other structures. So
no, but that
so here,
set of objects of a category is not a thing of the category. Like it's not a well-defined. So I'm confused about them. Like we can use
sorry,
I'm confused.
Sorry, I'm not sure about your question. You mean the objects of the?
I can ask in the end. I think it's like I understand, but like I'm just confused about big picture. So I will ask Indian.
Oh, okay. So then we discuss morphisms between flow categories. So yeah, so we consider such a smooth map, and for critical points in M and critical points N and critical points in N, we want to equip such a pair with a modular space defined as this. So it counts this. So I start from P. After the flowing, it flows to another point R, and I use the map phi to map it to phi R, and consider the gradient flow on N, and it ends at Q. So I define the WPQ as this. And so as we assume all the transversality, we can show that this is a manifold, and its dimension can be calculated from the index of P and Q. So here, this picture can help you understand the space of WPQ better. Okay, and so this is the point P, and I denote this segment. I use this segment to denote the unstable manifold of P, and here it's an unstable manifold of Q on N, and I consider the WPU times N intersect with WQS times M, and consider the rectangle part here, and the intersection of this rectangle and the image of F is a space WPQ. Okay, so I claim that such a WPQ can be used to define morphisms, can be used to define a chain morphism between the Morse chain complexes by just counting them. Okay, so now it's the time to define the Morse morphism between the flow categories. So it's nothing new. It just given flow category M and N, and so in now we assume that M and N are just given from a Morse function on a finite dimension manifold, and we equipped for each critical point X on M and each critical point Y on N. We equipped it with a manifold with corners WXY, which is defined as above. Moreover, I claim that such W is a left modular over M and a right modular over N, and so the embedding can be studied as following. X prime, Y, so I claim that the trajectories in WXY may be broken into these two parts when this trajectory is very close to x prime. So this how do you define these two maps by such a broken process? So okay, so now let's come to the cobordis, but so this page and the next page is my own understanding of what we are going to do next. I'm not sure they are definitely right, but I would like to tell you my own understanding. So first, I claim that the homotopy preserves the morphisms between most homologies. And if I have a homotopy n times I to another manifold n, and so on the m times 0, your map phi induces a morphism between flow category. I use W to denote m times 0 by 0 psi to and in the bottom you have another you have another morphism between flow categories. And if we for the whole m times I, you have you still have a morphism between the flow categories, but the dimension of this phi star is one more than the dimension of phi star 0 and phi star 1. So if I denote this W, denote this V, and denote this R, I claim that your partial R should be the union of W and V and the broken trajectories of R. So anyway, here the cobordism between two morphisms is something of one more dimension series of manifolds.
Sorry,
Okay.
can you
Please.
give a description of R, like as flow lines as you give to the other manifolds?
So so the R so let me begin. So now we have the M F1 to N F2. So we have a map phi 0 and And if I would consider M times I, so if you see here, so the function on M is f1, and you can naturally get a function f1 on M times I, and I can perturb it to make it Morse. And the phi here is a smooth map between manifolds with Morse functions. So phi induces the on flow categories of M times I. So this is the flow category. This is another flow category. And if we when we perturbing the F1, we may so this is M and this is your I. Here is F, and I use T to denote the I component, and I consider the F plus epsilon T. I consider is this? Oh yeah, I consider yeah, I should consider F plus yeah, I should consider F plus epsilon T squared to make it Morse. And the critical point of this functional on M times I is the same as the critical point of the Morse functional on M. And so this Rxy, the X in Rxy, can be considered as a critical point in M. And moreover, so after this perturbation, you may imagine your gradient flows as something like this. So that's why I said that the boundary. Oh, sorry, I hit the wrong direction. So the gradient flow looks like this. So that's why I said that your Rxy has a boundary of the zeros level and the 1 level. So does this answer your question? Okay.
Yeah, thanks.
So now in the end we consider the composition of morphisms. Now if we have two morphisms between smooth manifolds, and of course we ask them to equip with Morse functions, and we have the morphism W and V. So for each critical point X in for each critical point X in M and Z in L, I define a manifold with corners UXZ as this. So I will then explain you why do we want to define this and modular equivalent relation, and this relation is given by this, and where the C is an embedding map defined as above. So that's a definition of the composition, but then I will show you a picture. But before I show you the picture, I claim that if I want to define the morphisms between the Morse homologies using such U, and the morphisms between Morse homologies by just the composition of the smooth maps, they are the same. So okay, let's see the picture explaining the composition. So the map, the manifold UXZ consider 3 parts. So usually it's from M from P from X to some point P, and after phi is mapped to some phi P, and flow it to point Y, and from Y it flowed to a point Q, and after your map C, this is Q and is flowed to another point Z. So that's what you want to have in UXZ. But you recall that we moduli such a relation. So what's this relation? So if when our flow goes into in the manifold N, and it breaks into multiple parts, then I have two ways to present such a flow above. So either I consider this part and this part as our first part, this part and this part as our second part, or we can consider this part and this part as our first part, and this part and the left one the second part. So we have two ways to describe it in WXY times NYZ for different Y. So one in this and one in WXY prime times NY prime Z. We want these two ways to be the same. So when we define the composition of the morphisms, we need to modulate such a relation. Okay, so that's all of the first part. So I introduced the definition, or maybe not definition, but construct a flow category for the Morse theory. So any questions up to now?
Maybe it's too much details, but the W's and V's, like the morphism between flow categories, are manifold with corners, or which type of manifold?
Yeah, I will.
Of them?
Yeah, so let me let's skip to something near to the end. Yeah, so I will explain that the definition. So it's not a strict definition. So when we're trying to glue the when we're trying to glue the different, so when we quote the equivalence relation, we glue other things together. We need it to be smooth. So this is not a trivial thing to glue the manifold with corners into a smooth, bigger manifold. So to define the smoothness or the smooth structure, we need the system of corners. But it contains a lot of details, and I don't want to introduce it here. So we omit it, and we just think and here the gluing is just a topological gluing, but don't consider its smoothness. So, and the smoothness is why we need to introduce the system of color.
Okay, thanks.
Okay. So let's continue. And so so we before the formal definition of the flow category, we want to do some more detailed discussion about the manifold with corners. So we recorded the definition of the manifold with corners is that it's locally homomorphic to this guy, and let K here to be called K here to be the codimension of a point P. So a manifold with faces So the definition of the manifold with faces is as following. So if the closure of each connected component is a manifold with corners, then it's called a manifold with faces. And we call the such component a face, and a face of codimension 1 is a boundary face. So anyway, let's see a picture again. So in this cube, so it's a solid cube, and a point on its edge, so it's a point of codimension 2, and the component of the component of this codimension 2 submanifold its closer is a segment. It's a manifold with corners. So you can check other submanifolds to see that your cube is a manifold with faces. But if we consider such a drop, so this part is smooth, but it has a singularity here, and of course it's solid. And if we consider such a face, if we consider such a submanifold, and its closure is something with singularity, so it's not a manifold with faces anymore. So to understand the manifold with faces, we can understand it as a simplicial complex comparing to the CW complex. You know that when you define your CW complex, you can glue in things arbitrarily. But when you define your simplicial complex, you need to define you need to glue your simplexes sides by sides, and they can't be too close. So that's how to understand the manifold with faces. Okay, and here there are some other theorems to help you understand it better. So if M is a manifold with faces, then locally it must looks like a looks like a corner of a cube. So you can see that a point here is codimension 2, and it will be on the boundary of 2 codimension 1 faces, and this one is on the boundary of 3 codimension 1 faces. But for your drop, this one, this point, it should be codimension 2, but it's on the boundary of only 1 codimension 1 face. Okay, and I claim that the intersection of 2 faces is a union of several faces. It's easy to understand. So then we introduce the system of faces. So yes, this is its definition, and I want to divide the faces of different dimension into several families. Anyway, let's say a picture is better to understand. So let's consider such a cube. Such a square, a solid square, is a manifold with corners. It's even a manifold with faces. And the codimension 1 face, there are 4 connected components, and I divide them into several pieces of embedded manifold with corners. This one, and I divide its codimension 2 faces 4 points into 4 sets, and a system of such a thing is called a system of faces. Yeah. So that's why I said here. That's what I said here.
Wait. The picture that you just draw,
Yeah.
is just the right upper point need to be in like 2 faces because it's codimension 2. Or this is not a manifold with corners.
Oh no.
About?
Yeah. I understand what you said. So yeah, you are right. So this manifold itself is not a this manifold itself is not a manifold with corners. Yeah, you are right. I made a mistake here. So I wanted to simplify some definitions. So in fact the definition is a little more complicated. I should if I want to correct it here, I shouldn't write it as I Yeah. You're right. I should I should say that so each set in my system of phase, it's a union of some manifold with phases. It can yeah it doesn't need to be only one. It doesn't need to be only one whole manifold with phases. Yeah. Thank you for your correction. I needed to change the definition here. But anyway, a system of phases is such a thing. So I think this example can tell you what it is essentially. Okay, so let's come to the general definition of flow categories. So let's try to put the things in the first. Let's try to rewrite the things in the first part into abstract language. So a flow category M is defined by a finite set of objects with an index map. And for any 2 points x and y, the morphism is a manifold with phases. Note that so note it's not only a manifold with corners, but with phases of dimension, of the dimension it should be. And I ask that there exists the associated map as before. Oh, maybe I forget. Yeah. So I forgot a very important sentence here. So I asked that the order image of C is a system of phases. So if I want to translate this into the language of Morse theory, it says that any boundary point of MXZ lies in the products of lower dimension manifold in moduli realized as moduli spaces. Okay, and this is just what we already said, compactification. In Morse theory. So that's a general definition of a flow category. Okay, any questions? Or if no, so let's continue. Let's continue to translate everything in the first part into the category language. So yeah, we just like what we did in the first part, we can define the morphisms of flow categories. And so a morphism W from M to N is for a given X in objects M and Y in objects N. We give it a manifold with faces WXY. And we have such we defined such a composition. And I didn't write it out here, but this map satisfies all the possibility associativity. So that means if I consider M times M X prime Y X Y. So if these three products satisfy the associativity. So if we calculate the product here first, the same as calculate the product here first. Oh, sorry. And I ask you to satisfy that, and I moreover I need all the boundary all the boundaries in this form gives you a system of faces. So at time is a little tight. So here are the examples. We just see the most important example. So just by definition, if I have two morphisms, just by disjoint union pointwisely, you can get a morphism from the you can get another morphism by disjoint union. Okay, so let's go to the properties. So given two flow categories and W and V2 morphisms, so a cobordis between them is a one dimension higher manifold Rxy, one dimension higher, and we have the embeddings. So it's just a pointwisely cobordism, but we have just pointwisely cobordism, but we have such embeddings from the system of faces. Yeah, so that's a cobordism. And for two categories, we can naturally consider the such a group, the set of all morphisms between them, but modulo the cobordant, as what we did in algebraic topology. And I claim that under the disjoint union, the elements of the cobordism of their morphisms from a group. So the only a little non-trivial thing is about the inverse to prove this lemma. We claim that if phi is a map from M to N, then phi times I is a map from M times I to N. So here times I means that I multiple every element in M interval. So that's M and M itself are covariant. Covariant. So M plus M equals to 0. And the elements here, it forms a group. Okay, so let's come to the composition of the Morrison. So it's totally the same as what we did in the Morse case. And we omitted here. Okay, I claim that such a composition define the map between the define a composition of maps between the flow categories. Okay, so that's a remark I just mentioned. All we did here, such a gluing, we just do it topologically. But that's not what we want. We want to glue everything smoothly. So that's why in the paper, they introduced the system of collars. But to read that paper, we don't need to understand it totally. Okay, so we define what's a single flow category, and we define the Morrison between them by modulo the covariance. And we define the composition as above. So all these together, it forms a category called the category of flow categories. Okay, so that's my main task today, and I list the conjecture of Abzai and Bloomberg here. So they have a totally description of the category of flow categories. Okay, and so here in the left 5 videos, I would introduce some other structures on the flow category. So first is bilinear maps. So it's all the same as before, but now I have a map from M times N to L, but not only M to L. And as before, for each pair X, Y, Z, sorry, for each triple X, Y, Z, we equipped it with a manifold with phase. And we have the composition map. They are compatible with each other, associative, and they define a system of phases. So, and moreover, all the discussed above, we don't consider the orientation, but you can frame everything. So a stable framing is a direct sum of, so just like the Morse case, in the Morse case, your Vx is your Vx is your Tx of the is your M minus the direction W unstable P. Yeah, so in the Morse case, your Vx is this guy. And by flowing, as what Philip said in the last talk, we would have such stable algorithms. and we in fact we can frame everything, including the morphisms, the composition of the morphisms, and the coordinates, and everything. We can frame it, but the time is not enough, so I skip that. And finally, after framing everything, we get the framed category of flow categories. And we have the Abzai-Bloomberg conjecture for the framed case. And it says that it's equivalent to the homotopy category of finite spectra, which is really surprising. And here said it's a totally topological thing, but this side is a differential or something geometry thing. Okay, so that's all I prepared for today. And any questions?
Let's start with thanking Jianqiao again. That was a great talk. And if we can stop the recording, we can have some questions.
I'm still a little bit confusing. So maybe I can ask for a specific example that will elaborate things. So if you take, for example, like 3 flow categories with 3 objects, like 3 on 3 dots.
You mean three objects for each of them, right?
Yeah, like
3. Okay.
Yeah, exactly. And you have like a W from M to N and V from N to L.
Okay.
I'm trying to understand what is the like faces or corner structure of V and W, and how to glue them to be like the same type of corners.
You mean you are understanding you are trying to understanding the composition of W and V, right?
Yeah, exactly. Like you define like what we call like U, which kind of like multiplication, like Cartesian product, and then some relations. But somehow I'm like every time I'm confused of the type of like the result, like why the type of the result in terms of corners have the same type as W and V.
Okay. Sorry. You said that it has the same type as W and V. So, you mean that YU is a manifold with faces, or your choice, or you doesn't rely on the properties classes, you mean?
Yeah, I mean, I suspect that we can say something like V is a manifold with such and such faces, and W is a manifold with such and such faces in terms of the number of objects.
Okay.
And okay, maybe it's like too much now, but like, can you say something about the corner structure of W? Like how much faces W have in this case?
First you need to, I mean, for this example, you need to equip any morphisms between them a manifold structure. Then we can discuss other things. Or may we try to discuss it in the Morse setting? Which one do you prefer?
Any of them. I mean, I hope which they will be the same. Like the theoretic one need to be compatible with the Morse one.
First the corners of W, so it comes from.
Oh, sorry, please forget to stop the recording.